Hello, this is going to be my first review video. If you guys enjoyed the video or thought it was helpful, please leave a comment. And if you have any recommendations for next video, because I want to make this a more common thing after spring break, just leave a comment in the comment section, or you can send me an email. So the first video is going to be on energetics. The first thing that we're going to be talking about is Gibbs's free energy. And remember, Gibbs free energy is defined by the equation delta G, which is Gibbs's free energy, or the change in Gibbs's free energy, equals delta H minus T times delta S. And if we remind ourselves what the equations are, or what each variable in the equation is, delta H is enthalpy, and you can remember it because enthalpy has an H in it. And then we have S, which is entropy. And then remember that enthalpy is the energy in the bonds. Energy in bonds. And then entropy is disorder. Okay. And then, okay, minor technical difficulties. My video got cut off, but so basically what I drew is there are two graphs, graph A and graph B, and we know that it's indicating delta G because the graph on the y-axis is defined by a change in free energy. It'll say free energy on the side, and then on the x-axis it'll be time. Time taken place in the reaction. So then we have two types of reactions. We have an exergonic reaction and an endergonic reaction. The easy way I like to remember it is that for exergonic reactions, you're exiting the system, so energy exits, which means that the amount that you start with is higher than what you ended with because you lost energy. Whereas with endergonic reactions, you're putting energy into the system. And if you put energy into the system, the amount of energy that you end up with is higher than what you originally started with. So then if we look at graphs A and B, in graph A, if your free energy originally starts at this point right here, and then you move up the curve and you end up with more energy than you originally started, we can say that this is an endergonic reaction. Whereas in graph B, you start off at this point right here, and then over time you move down to a lower amount of free energy than what you started with. Therefore, in graph B, we're losing energy, which means that energy is exiting the system, and it's an exergonic reaction. And so if we look at this, we can tell that the change in delta S is positive because we originally start off with a very ordered molecule in that the atoms are really close together, and then they eventually spread out, and because they're spreading out, we're increasing the disorder in the system, and that makes delta S positive. And then if you remember back in lecture when we talk about an increase in delta H, we can tell that delta H is increasing because it is related to electronegativity. Remember that with electronegativity, if we increase electronegativity, the atoms are closer together. And that's what I tried drawing there. That the atoms are closer because the electronegativity has increased. And if the electronegativity increases, remember that the energy in your bonds decreases because the atoms are closer together. And then so if you wanted the opposite effect, then if you decrease the electronegativity and you have the atoms further apart from each other, we would have more energy in bonds, which would mean that the delta H would be increasing. But in this example right here that I wrote out, where the electronegativity increases and the energy in the bonds decreases, your delta H would be negative. And then so let's go through a really quick example of 3 separate equations, and we're going to try to figure out if they're exergonic or endergonic. So remember, exergonic energy is exiting the system, so you end up with a lower amount, whereas with endergonic, energy is going into the system, and you're increasing the amount of energy. And so if we look at equation 1, the delta G for equation 1 is negative 7 kilocalories per mole. And if delta G is negative, that means that energy is leaving the system, therefore equation 1 is an exergonic. Okay, now let's look at the delta G for equation 2. Oops, I thought that would highlight. Okay, I guess we'll highlight. So, look at delta G for equation 2, negative 14.8. So it's negative again. The negative sign implies that energy is leaving the system. Therefore, equation 2 is also an exergonic reaction. And then lastly, if we look at the delta G for equation 3, we see that it's positive 3, which means that energy is being added to the system. Therefore, it is an endergonic, because energy is entering the system. And remember, if we talk about, let's just make up a reaction. So A plus B plus energy leads to C. So remember, when we read reactions, we read from left to right. So these are your reactants, and C is your product. So if we are adding energy to the reactants, that means we're putting energy into the system. Therefore, this is also another way we could write an endergonic reaction. And we would expect this reaction to have a positive delta G. And this reaction should be non-spontaneous, because we had to add energy to the system. Whereas, if we wanted to write an example of an exergonic reaction, we could write A plus B creates C plus energy, as in there's a release of energy. So this is your exergonic reaction. Delta G is negative because you're getting a release of energy, and it's a spontaneous reaction. So remember, for exergonic reactions, they're spontaneous reactions, whereas for endergonic reactions, we have non-spontaneous reactions. Okay, so I think the best way to memorize this table is to actually plug variables in depending on what the circumstances. So let's take a look at the first box where delta H is less than 0. If delta H is less than 0, that means it must be negative. So let's just say delta H is, let's say for example, -4. So if delta H is -4, and let's say the reaction runs at 273 degrees Kelvin, so then you would get 273 times, and then let's just say delta S is, let's just say 4 as well. So then we take 273 times 4, and whatever that number is, 4 minus 273 times 4. Let me take my calculator out. 273 times 4, 1092. So then we have -4 minus 1092. So -4 minus 1092. I don't know why I had to pull my calculator for that. Which should be -1096. And the negative symbol implies that delta G is, this -1096 equals delta G. And because it's negative, delta G is negative, that means that the reaction is spontaneous. And then, so that proves that the reaction is spontaneous at all temperatures. You can plug in any set of numbers for this. So then let's try non-spontaneous at all temperatures. When delta H is greater than 0, if delta H is greater than 0, that means it's a positive number. So let's just say it's 60. And let's just say the temperature is again 273. And delta S is now -4. So then we would have 60 plus 273 times 4. Which is, again, 1092. And because of this, you're going to get 60 plus 1092, and you get 1152. And this is a positive number. So delta G is positive again. Therefore, it is non-spontaneous, because remember, non-spontaneous reactions are endergonic reactions in that they require energy to be put into the system. So hopefully that helps. If you guys want any other videos clarifying further topics, just let me know. But I think the biggest thing is you should be able to go over this table, memorize it, and then be able to talk about the variety of instances in which delta H and delta S will vary. And I think that putting numbers into the actual equation will help you guys with that. So I hope that helps. Thanks.